Hello, Professor Kleinium here. We recently took a stoichiometry test in class, and I want to go over the test with you here via this podcast. Let's see how you do. Now, the only thing I need to solve this is, of course, I need my calculator, and I need to have a periodic table. I've got this little portable one here, and notice it's the very simple periodic table. All I need is the molar masses below the symbol, and I'm good to go. So frankly, that's all the resource you need is the periodic table and a calculator. Okay, so here we go. Let's look at the first problem here. Alright, so in a balanced chemical equation, the molar ratio of two reactants is determined from the... Now the key word here is the molar ratio. Molar ratio is, for example, in a balanced chemical reaction, as you recall, you've got these little coefficients that sit in front of the reactants and the products. These numbers right here, called coefficients, they are the mole ratios, and they are the ones that determine in a balanced chemical reaction what the quantities of reactants and products will be. So the answer here is A. Okay, what is the molar mass of copper 2 chloride? Okay, so copper, the symbol is Cu. The little 2 here means that there's a +2 charge on the copper. Chloride, as you know, is the symbol Cl, and as an atom, as an ion, it has a -1 charge. So for this, you have to, before you solve the problem, you have to balance the charges. Now I'm going to need to multiply this one by 2 because -1 times 2 is equal to +2. So first of all, what is the formula? It's going to be copper, chloride, and the little 2 here. A lot of people forget that, and that messes you up. You need to have 3 atoms here, 1 copper and 2 chlorides. So looking at the masses of these up on the periodic table, I see the mass of this one is 63.5. The mass of this one is 35.5. But that's times 2 for a total of 71. So 71 plus 63.5 is, what does that come out to? So checking my calculator, I get 63.5 plus 71, 134.5. Okay, it appears that the answer is E here. All right, 134.5. Which concept allows you to relate the coefficients in a balanced chemical reaction to actual amounts of reactants and products? Okay, like in the same vein as question number 1, question number 3 is really talking about the mole ratio. Because without the mole ratio, these numbers in front, the 2 and the 1, like I'm showing you here, you cannot determine the actual amounts of anything. Every chemical problem has a mole ratio, so that's really the heart of it. And the coefficients, of course, are the ratio we're talking about. Okay. So advance the test a little bit here. Let's go to problem 4 and 5. Alright, so problem number 4. See how many moles of aluminum are needed to react completely with 8.9 moles of FeO. So first of all, I notice that FeO is this. And the question is, how many moles of aluminum? So get this straight in your mind, first of all. What are we looking for? And we're given 8.9 moles of this. Part of the problem here is this is not a balanced equation, so let's go ahead and balance that. I have 2 aluminums here. I'm going to need to put a 2 in front of here to balance aluminums. I've got 3 oxygens. I'll put a 3 here to balance the oxygens, and of course I need a 3 here. And that's just going to be a 1. So this is the mole ratio we're talking about, starting out with 8.9 moles of FeO. So writing that out, let's go ahead and start with the 8.9 moles of FeO. That's iron Roman numeral 2 oxide. Okay, so we're not starting with grams here, and the answer is not going to be in grams, so we do not need to use a molar mass here to do any conversion. We just have to use the mole ratio to convert this. So that means we go back to these numbers. Okay, first of all, look at this right here, FeO. So that's this. It has a 3 in front of it. That needs to go down here below to cancel. So 3 moles of FeO. And now we're looking for aluminum. We want to find out how much aluminum is needed. So that means the one on the top is now going to be moles of aluminum. And there's a 2 in front of that, so I'm going to need to do this. The answers all appear to be in moles, so I can solve it right now. I don't have to convert to grams of aluminum. It's just a mole ratio between moles of this, so the answer is going to be 8.9 times 2 equals divide by 3 equals. So let's do that. In the calculator, I'm going to put in 8.9, which is really close to 9, times 2 equals divide by 3 equals about 6 moles. Let me do that one more time. 8.9 times 2 equals divide by 3 equals, 5.9 moles. So the answer is going to be B here, 5.9 moles. Okay, what is the limiting reactant if 2.6 moles of aluminum? So this is something we're given, and we're also given this amount. So if you're given a little bit of both of the reactants, one of these is liable to run out first, meaning the limiting reactant is the one that we have too little of, because as you know, anytime you're cooking something, you might run out of one of the ingredients first. So if you have a limiting reactant problem, you're going to need to solve both of these reactants for either of the 2 given products, and I can go from moles to moles this time because grams don't even appear in this problem. So first of all, let's solve this in terms of 2.6 moles of aluminum, and get in the habit of writing these out just like I'm doing here completely. This is going to help you to develop your muscle memory to be able to do this correctly. So it's going to be 2 moles of aluminum. So notice moles of aluminum are going to cancel. And then I have to solve this for one of the 2 products. Either product works. I'm going to go ahead and solve it for hydrogen. The goal here is to find out which is going to make the lesser amount of product. So that's one half of the problem. The other half of the problem I'll set up. I have 5.2 moles of HCl. Okay, so that's good. And I'm going to find out how much of the same product. So I'm solving for the same product. This is going to be 6 moles of HCl. We'll create 3 moles of hydrogen. So see, this is 3 moles of hydrogen here too, 3 moles of hydrogen. So really I'm now going to compare both of these to the same exact product. And then I can determine which is the limiting reactant. So let me go ahead and do the math first of all. Well, 2.6 times 3 equals, divide by 2 equals. Okay, I get 3.9 for this first one. Moles of the product hydrogen. Okay, and the other one I've got 5.2 times 3 equals, divide by 6 equals. I have 2.6 moles of hydrogen. So now I need to compare these 2 numbers. 3.9 compared to 2.6. These are the same product, so now I can see that I actually made less product with the hydrogen chloride. Okay, so then the question is, what is the limiting reactant? It's not the hydrogen, that's a product. The limiting reactant is this thing over here, the hydrogen chloride. Therefore, the answer must be B. Okay, run through this again. every time you do a limiting reactant problem, you have to solve for both of the reactants. Solve for one of the products, either one will work, and then look and see which one makes the lesser amount of product. So this one cannot happen. That's not the theoretical amount you could make. This is the total theoretical amount you could make given these two reactants. Okay? The limiting reactant is the hydrogen chloride, because that is a reactant. So don't make the mistake of circling this and saying, well, that's the reactant. That's actually the product. Okay. So let's advance the test now to the next page. A couple of multiple choice questions. Should go kind of fast here. So in a balanced chemical reaction, how do you determine the limiting reactant? Well, we just saw the case where you check to see which reactant produces the least amount of product. We just saw that in the last problem. So that has to be the answer, A. Now the excess reactant. So you have the limiting reactant, and the other one is called the excess reactant. It's the one you waste or you have too much of. So it's the one that you're going to have something left over when the reaction is over with. Answer is A. Okay, the next one. Methane burns in oxygen to form the following equation. I've kind of cut off some of the answers here, but maybe we have the right answer. So let's go ahead and solve it. Now here, this is a little more complicated because it's grams here to grams. So the other problems on this test were just moles to moles, but this time I have to, when I solve it, I have to go the next step. I have to start out with the grams of both of these reactants. So this is another limiting reactant type problem. We have to figure out which is the limiting reactant first. So first of all, I'm going to do the same type of calculation as I did before. This is with methane. Now the molar mass of methane is 12, 13, 14, 15, 16. The number 16 comes from the periodic table. It's the sum of the masses of all 5 of these atoms. Okay, so that is equal to 1 mole of this reactant CH4. Okay, so far so good. Now I have to do the mole ratio. That you have to do that in every problem. So I have to go back up to the balanced chemical equation. I see it's a 1, a 2, a 1, and a 2. So that becomes critical at this point. It's a 1, 2, and I'm going to solve for CO2 here because it's mentioned. So it's a 1-to-1 ratio. 1 mole of our reactant we're looking at will make 1 mole of the product CO2. Okay, excellent. Now how many grams of CO2? So then I'm forced to go back to grams. This step is necessary, but it's easy. 1 mole of CO2, here's where you put in the molar mass of it, is equal to 44 grams of CO2. Again, this is just a periodic table thing. Carbon is 12, oxygen is 16. 16 times 2 plus 12 is 44. Okay, now we got to do the math in this longer problem. And the way you solve this is you'd say 28.3 divided by 16 equals times 1 divided by 1 times 44 equals. So for this problem, let's call it a sub-problem, I have 77.8. So 77.8 grams of CO2. Now that's not our final answer yet, although I do take note of, if that's the correct answer, there it is, part D. We have to eliminate one other thing. We have to solve this for oxygen, because if oxygen runs out first, then this is not going to be the correct amount. So now we're going to do the whole thing with oxygen, and so 140.8 grams of oxygen. Alright, so the first step is this molar mass step. And again, put in all the steps here. So it's 32 grams of oxygen is 1 mole of oxygen. And here we're going to do the mole ratio. Down here is where we put the oxygen. And I'm going to solve for the same thing again, carbon dioxide. And here the ratio is 2 to 1. So 2 moles of oxygen is 1 mole. So see, there's where the mole ratio comes in. If you forget to divide by 2, you're stuck. Okay, And then I have to solve for grams of CO2. So really, I have to multiply, just like I did above. This is identical to the above step. 1 mole of CO2. Okay, so let's go ahead and solve that. I have 140.8 grams divided by 32 equals, divided by 2 equals, times 44 equals. Okay, now I get 96.8. All right, so 96.8 grams of CO2. Now we can answer the problem. Because, first of all, we figure out what the limiting reactant is. Well, I know what it is, because 77 is less than 96, so the limiting reactant, of course, is the methane. It's going to produce less product. That means that this is never going to happen unless we add some more methane, CH4. The real answer, therefore, is D, 77.8 grams. Okay, very good. Let's go ahead and advance the test a little bit more. All right, so what is the maximum amount of ozone that can be produced from 16 grams of oxygen? So here is our balanced chemical reaction. Notice the coefficients are important. Notice this is O2 and O3. This is our reactant. This is our product. Okay, so I'm starting out with grams of oxygen. So that has to be the reactant. And how many, I'm going to see, I have grams, I can see in the answers, grams of ozone. So if you can see, I'm going to start out with grams of oxygen. And then way over here, I'm going to put grams of ozone, that's O3. So somehow I have to get from here to here using our standardized kind of procedure. So 16 grams, go ahead and put that in. 16.0 grams. Now here is where I convert from grams to moles. All right, so 16.0 grams of O2. I know that O2 is 32 grams of O2. O2 and 32 have to agree. Don't forget, it's the periodic table. This oxygen is 16 times 2 is 1 mole of O2. Okay, great. And then I've got to do the mole ratio. It's 3 moles of O2 make 2 moles of O3. So the 3 moles goes down here. You always remember where to put the 3 because you see these have to cancel. So the 3 cannot go up there. It's going to make 2 moles of O3. So now we're almost finished. Notice I've got to go from moles of O3 to grams of O3. Now to do that, I need the molar mass of O3. 1 mole of O3 is equal to 48 grams of O3. Where did I get 48? Well, oxygen is 16 on the periodic table. I've got 3 of them. So now I can solve for this. It's going to be 16 divided by 32. So 16 divided by 32 equals, times 2 equals, divide by 3 equals, times 48 equals, I get 16 grams. How crazy is that? 16 grams will make 16 grams. So the answer is D. After I do the math, I get 16 grams of O2. And when carbon burns in plentiful supply of air, that means you've got plenty of oxygen. What is the product formed? Now, one of the clues is this is one of the products of normal combustion. In normal combustion, you have 2 products. You have CO2 and you have H2O. Okay, so these are the normal products, meaning which is going to happen when carbon burns in the air. You're going to get carbon and oxygen. And given this hint I have here, the only possible answer is, of course, carbon dioxide. So carbon dioxide is the one that's going to be the answer there. Okay, very good. Let's advance the test again to the last few problems. What is the molar mass of chromium sulfate? Okay, so chromium sulfate, the molar mass again is the periodic table thing. I have to figure that a chromium is equal to almost 52, let's say 51.9. I've got 2 of them, so that's going to be 51.9 times 2. Then I've got this sulfate, but I see I have 3 sulfates. That means I have S times 3. So for the sulfur, I'm going to have this whole thing. Okay, now sulfur is 32.1 on the periodic table times 3. And then the oxygen, I have 4 times 3. Oxygen, I've got a lot of. I've got 4 times 3, that's 12. Times, well, of course, the molar mass of oxygen, 16. So 16 times 12 will be that one. All right, we've got a lot of mass here. Now, taking my calculator, first of all, I take 51.9 times 2 equals, all right, well, that little piece right there is 103.8. What's 32 times 3? Okay, check that out. 32.1 times 3 equals, that one is 96 right here. And then 16 times 12 is equal to 192. So I'm forced to add up all 3 of those. 192 plus 96 equals plus, I guess it was 103. I get 392, which is close enough to this answer right here. So you can see the answer is going to be this one right here, 392 grams per mole. That appears to be answer D. Okay, now this is a quick one here. The limiting reactant in a completing chemical reaction will be the substance that's completely used up. It's going to limit the amount of product. Okay, the chemical formula for aspirin. If you add up the molar mass of 9 carbons and 8 hydrogens and 4 oxygens, you will find out that it's 180 grams. Okay, so at 180 grams, the question is, what is 1.9 moles? So 1.9 moles of aspirin, C98804, okay, I have to convert this to grams. So moles are in the bottom. 1 mole of this is going to be equal to 180 grams. So my pen's starting to give out here, so I'm going to abbreviate this a little bit. The answer is going to be 1.9 times 180. I can see now that's a large number. So the answer is going to have to be this large number right here, 342. Okay, in a chemical reaction, the mass of the products, well, you don't lose any mass, so it's going to have to be equal to. And so let's go ahead and advance the test here a little bit more, almost to the end here. Okay, what happens to carbon in a candle when the candle burns? So the carbon in the candle, the carbon becomes carbon dioxide, which, as you know, is given off as a vapor. So the best possible answer here is that it becomes a part of a compound, namely CO2, which goes into the air. When magnesium reacts with oxygen in the air to produce magnesium oxide, it's going to weigh more because you have now an added oxygen. So you start out with just magnesium. Well, magnesium oxide obviously is going to weigh more than just magnesium by itself. Okay, and then the final answer, and then we have this free response question. So let's take a look at this one. Here we have which of these mole ratios would work. So notice in the answer, 4 has to go with aluminum, and 3 has to go with oxygen, and 2 has to go with that. Any other variant will not be right. So my eyes are immediately going to this one, where 4 goes with aluminum and 3 goes with oxygen. See, that's correct. For instance, this one is wrong because 4 goes with aluminum, that's right, but 2 does not go with oxygen, you see. So all of the rest of these are wrong. The correct answer is D. Okay, so finally let's do this sort of a free response question here. These are the most important ones. These are the ones I'll probably like to put on a retake for sure. All right, so identify the limiting reactant for this equation. Well, okay, now to remember what we did on that. First of all, we realize we have 6 moles of this, and we have 7.5 moles of this. All right, well, we have to solve both of these for the same product. Now, it doesn't say anything about grams anywhere in this process, so I don't actually have to worry about grams at any point. But let's go ahead and do the first one. The limiting reactant, first of all, let's solve 6.0 moles of aluminum. Okay, now we have to do the mole ratio here. So 2 moles of aluminum, and I can go right to the product now, is going to make 2 moles of this product. There's only one product, but remember, you just have to solve for any of the products. It doesn't matter. This is going to tell me how much in terms of moles of product. So it's really 6 times 2 over 2. I'm going to make 6 moles of product here. So keep that in mind. Now I have to solve for the next one. 7.5 moles of, this time it's Cl2. Okay, and now let's work in the mole ratio here. Here the mole ratio is 3 moles of Cl2 will make 2 moles of product. And so here we have 7.5 times 2 divided by 3. Let's get an exact amount on that. 7.5 times 2 equals, divided by 3 equals, so here I can only make 5 moles of product. All right, now we know the limiting reactant because it's the one that made the less amount of product. So, but this is not the answer. The answer is Cl2 is the limiting reactant. So let me write that in here. Cl2 is the limiting reactant. Okay, so then why? Because it made the lesser amount of product. Determine from your answer above what the number of moles of product would theoretically be formed. The problem is you have to decide between these two amounts. You can never make the 6 moles because you've actually run out of aluminum. So the true answer is 5 moles of product will be made. My pen is giving out here, so I'll have to kind of abbreviate this. Because 5 moles is the lesser amount of product, and Cl2 is determining the amount of product made. So that's the correct answer. And finally, if the reaction yields 4.3 moles, this would be a lab value. What is the percent yield? Well, you put the lab value over the theoretical value times 100. Okay, so the lab value, 4.3, divided by the theoretical value, which is what we determined here, it's 5.0, multiply that by 100, gives you the percent yield. So what that means is you take 4.3, you divide by 5 equals times 100, and of course you know how to do percentages. I get 86% yield. Okay, so that's the end of the test. Hopefully that was very helpful.